Dear distinguished experts, I am Ren Shuai from the GNSS Laboratory of Universidad Malaysia Pahang Sultan Abdullah Wempasar. Today, I am honored to present our research entitled CEEMDAN-BiLSTM for Landslide Displacement Prediction, Exploring Rainfall, Hysteresis, and Effective Rainfall Cycles. Landslides are among the most severe geological disasters worldwide, causing between 5,000 and 10,000 fatalities annually and inflicting substantial damage on both human society and the natural environment. The global economic losses from landslides are estimated to exceed $4 billion per year. Therefore, developing effective landslide early warning systems is of critical importance. Landslide displacement is a nonlinear and highly complex process, making it difficult to predict directly using conventional models. To overcome these limitations, this study proposes a CEEMDAN complete ensemble empirical mode decomposition with adaptive noise approach to decompose landslide displacement data into trend and periodic components. By introducing adaptive noise, CEEMDAN effectively mitigates the mode mixing problem inherent in traditional EMD methods. For the displacement prediction model, we adopt bidirectional, long short-term memory bias. While LSTM is widely recognized for its strength in time series prediction by capturing temporal dependencies through forward propagation, it cannot consider future information. The BiLSTM model addresses this limitation by integrating both forward and backward LSTM layers, enhancing its ability to learn complex temporal dependencies and improving generalization. The overall prediction workflow is as follows. 1. Use CEEMDAN to decompose the landslide displacement series into a trend component and periodic components. 2. Predict the trend component using a univariate BiLSTM model. 3. Identify external factors responsible for the periodic component, and employ Gray relational analysis (GRA) to evaluate the correlation between these factors and the periodic displacement. 4. Build a multivariate BiLSTM model to predict the periodic component. 5. Combine the two predictions to obtain the final displacement prediction. Evaluate model performance using RMSE, ME, and R. Data and effective rainfall modeling. The dataset used in this study is publicly available from the National Glacier, Permafrost, and Desert Data Center. The displacement records are monthly, totaling 120 observations, as illustrated in the figure. Previous studies have shown that rainfall significantly influences landslide displacement. However, most models only consider current month rainfall. In reality, due to soil infiltration characteristics, rainfall exhibits a hysteresis effect, where previous month's rainfall may still affect current displacement. To account for this, we incorporate an effective rainfall model to capture cumulative rainfall impacts and use it as a key influencing factor. Using CEEMDAN, the displacement data is decomposed into 5 intrinsic mode functions, IMFs, and a residual. The residual, representing long-term environmental trends, is treated as the trend component. The 5 IMFs, driven by seasonal and short-term influences, are combined and treated as the periodic component to reduce computational complexity. 4. Trend prediction, a BiLSTM model with 2 hidden layers, each containing 128 neurons, and a dropout rate of 0.2 is constructed. The performance results are RMS E igual a 3.81 mm, MAE igual a 3.23 mm, R al cuadrado igual a 0.98. This indicates high prediction accuracy due to effective decomposition. We categorized external influencing factors into 3 groups: rainfall, reservoir, water level, and landslide status. A total of 11 candidate variables are selected. GRA is used to quantify their correlation with the periodic displacement, helping select high-quality input features. GRA results identify P7 effective rainfall with a lag of 6 months as the most relevant variable. Therefore, we select for highly correlated variables P2, P7, R2, and D2 across the three categories, and build a multivariate BiLSTM model for periodic component prediction. The results are RMS igual a 9.41 milímetros, Ma igual a 7.69 milímetros, R al cuadrado igual a 0.97. This confirms a good fit between prediction and actual data. The final predicted displacement is obtained by summing the outputs of the trend and periodic component models. Compared with actual measurements, the results are R al cuadrado igual a 0.98, RMS igual a 10.7 milímetros, Ma igual a 8.77 milímetros. To verify the effectiveness of our proposed model, we conduct ablation experiments, comparing it with CEEMDAN-BiLSTM and CEEMDAN-BiLSTM models. As shown in the table, our model demonstrates superior accuracy. This study concludes that the effective rainfall hysteresis cycle in the study area is 6 months. The combination of CEEMDAN decomposition and BiLSTM modeling significantly improves prediction performance. However, several limitations remain. 1. The study is limited to open-source data from the Beishu River landslide site. 2. Regional, specific parameters should be incorporated for other study areas. 3. Future work should involve higher frequency datasets to further test and refine the model. That concludes my presentation. Thank you for your attention.